Hey, welcome back. In this video, we're going to begin the conversation of applying integration. As with any mathematical operation, it's fun to play with it just as a logical puzzle, but it's really important to see how you can apply it. In this video, we're going to start with a baseline application just to build this idea of what is the consequence, or how can we apply this infinite summation that we're working with. In order to help you tie the idea of integration into how we can apply it in the real world, I want to revisit this problem we had previously. If you remember, this was a context where we had a motorcycle. We were taking these 12-second intervals. We were reading the actual speedometer. And with that, we could get a general idea of the overall distance covered by this motorcycle. And again, we have these readings. These are speeds translated into feet per second. And in each case, we could get an estimate for how far that motorcycle has traveled for every 12-second interval. In this case, what I'm showing you is a representation of using the beginning velocity time. So let's look at a graphical representation of this. So if we plotted these points with time being the x-axis or horizontal axis, and then our velocity being the vertical axis, and then we apply the concept graphically of not thinking these as distances, but as these little areas of the interval, you can see what we're doing in the context of a graphical representation. The question then becomes, well, what if instead of these discrete readings, what if we had an equation that represented the velocity of this motorcycle at any given time? So using polynomial regression, what I did was created a function that pretty well represents these speeds. Then what should be clear is instead of having these discrete estimates for these intervals, if we take this velocity function and instead, if we integrate this function from 0 to 60, we will find not just this estimated distance, but we'll find the exact distance traveled by this motorcycle. Calculating this integral, all we need to use is the anti-power rule for each of these terms. So I get 0.0000134 t to the fourth divided by 4 minus 0.0065 t cubed divided by 3 minus 0.142 t squared over 2 plus 30t from 60 to 0. If you haven't realized it yet, what's really nice, if you're starting your interval at 0 and you have a polynomial, after you differentiate it, you'll always have, every term will have your t variable, which means when you plug in 0, nothing happens. You're subtracting 0. So to actually evaluate the distance traveled by this motorcycle on this interval, all we need to do now is to plug in 60 into this antiderivative. And when I did that, I got 1,509.8 feet. To me, this is a really important example. What I'm trying to model here is how you would investigate a problem and decide that integration would be a useful tool for solving that problem. And again, the idea is if I was given some discrete information about a function I'm looking at, what could I do with that in terms of these summations in multiplying over these smaller intervals with that idea? And again, well, if I multiply the speed times this time, that would give me distance because rate times time is distance. Knowing that, then I can realize that while it's nice and with these discrete points to get an estimate, if I want an exact value for what I'm looking for, whatever it is I'm trying to measure, in this case, distance, what I would need is a continuous function over this interval. And if I integrate over that interval on that continuous function, I'll have an exact value for whatever I'm trying to measure. In this case, the distance this motorcycle traveled from 0 to 60 seconds. All right, next thing is I want to investigate a little bit deeper some of the consequences of the fundamental theorem of calculus. First of all, the net change theorem. If you remember, the net change theorem is the second of the two statements that we find from the fundamental theorem. I've stated it a little bit differently in this case. So instead of saying antiderivative in original function, what I've stated is that in this case, if you have the rate of change function of a function and you integrate from a to b, you calculate that with f of b minus f of a. But more important to this statement is the fact that if I add over this f of a, At first, it might not seem like a significant consequence, but what this is saying, if we know about an initial state of a value, say we know something about a function, and we also know how it changes, but there's often when we have things like this, we won't know the original function, we just know how it's changing an initial value. You can calculate this f of b or some ending point value with the initial point of this f of a, the starting value or initial value, plus the integral of the rate of change function over from a to b. And also, just to continue this type of notation, small change I'm making here with the indefinite integral. If we apply the indefinite integral to the rate of change function, we'll get out the original function. And that's probably fairly clear at this point, talking about antiderivatives and derivatives. But importantly, like for contextual, in one case, like physics applications, if we integrate the acceleration function, what we get out is the function that this is describing the rate of change of. Specifically, that would be the velocity function. And then in the same way, if we apply the indefinite integral to the velocity function, we output the position function. And obviously, this idea of integration applies to any function that describes a rate of change, not just in physical applications like velocity, acceleration, and position. But I always think that this is the easiest way to ground yourself with a concept. Following all of this, the following also is true, and this relates back to that first example I was doing with the motorcycle, is that if you integrate a velocity function, or any rate of change function, but specifically a velocity function, you integrate from a to b, what you'll calculate is the net displacement of the object on the interval a to b. And if you haven't been in a physics class recently or ever, it's just important to state displacement, right? It's measuring a change in position. So it's not going to tell you a distance traveled. It's just going to say, hey, from here to here, what's the difference in that position? And just like velocity, it can take a negative or positive value. The negative or positive value mean whatever they represent in the context. As you'll see in the example coming up in a second, positive velocity will mean you're moving to the right of your original position or whatever, some origin point. Negative velocity will mean you're moving to the left. So a net displacement of, let's say, a positive 5 would mean you're 5 units to the right of the object. A negative 5 displacement would mean you're 5 units to the left. Then if we integrate the speed function, and the speed function, by the way, is always just the absolute value of the velocity function. The only difference between speed and velocity is this idea of direction. If we integrate the speed function or the absolute value of the velocity function, we won't get this displacement. We actually will get out the value of the total distance traveled on the interval AB. And these descriptions of the net displacement and total distance obviously come from the fact that we're using a velocity function. But again, these concepts relate in similar ways for any kind of rate of change function. But let's do an example here with this idea of net displacement and total distance, just so we get an idea, especially of how to deal with these absolute value integrals. All right, in this example, it's this classic context. We have a particle that's moving along a straight line, left and right. We'll say it doesn't matter if it's up and down, left and right, or at any angle. But we're going to say positive values of this velocity is moving to the right, and negative values of velocity is moving to the left. In this case, on the interval from 0 to 6, this is in seconds, meters per second is the output. We're asked to find the net displacement and the total distance. What you'll find almost always is that finding the net displacement is really straightforward. It's just integrating on the interval. The tricky part will be dealing with the absolute value and the total distance. But first, let's deal with this net displacement. So in this case, to find the net displacement, given this velocity function, we just need to integrate it on this interval from 0 to 6. And evaluating this polynomial integral is really easy in this case. We'll just use this anti-power rule again on each of these terms. This is going to be a t squared divided by 2, so I'm just going to write that as 6t squared. Evaluating from 0 to 6. And as previously stated, it's always really nice when plugging in a 0 into this expression after I've anti-differentiated with a polynomial, because I have nothing to subtract. This will be minus 0. All I need to do is plug in the 6 into this expression and evaluate. And when I did that, I got negative 36 meters. And then before we move on to distance, just to make sure we know what that means, negative 36 meters states that at the end of this interval, it's 36 meters to the left of where it was when it started. All right, let's do the fun of calculating the total distance. In this case, we're going to evaluate this integral on 0 to 6 of the absolute value of this velocity function. The absolute value is the important piece here. It's really important to state at this point is that we don't have any integral rules with absolute values, so we can't just evaluate it and apply the absolute value to say, hey, this answer is going to be a positive 36. It doesn't work like that. What I'm going to do first is just make sure we have this basic definition of the absolute value of a function. So if I take a function and apply the absolute value, written in a kind of loosely piecewise function here, this result, the absolute value of this function, will simply be the function itself when the function is positive, so the absolute value doesn't do anything, it outputs the actual values. When this function outputs negative values, it will output the opposite of that, because obviously those negative values are going to turn positive. So this statement right here would be a definition of the absolute value of any general function. So then what we're going to do, we did this a lot in differential calculus, is we now need to find out when this function is positive and when it's negative. And then we're going to split up this integral over the two intervals when it's positive and negative and make this adjustment. So what I'm going to do is just factor this and find the zeros. If I couldn't factor, I obviously could use other techniques to find these zeros, but this has been set up to be nice for us. This just factors into t times t minus 2 times t minus 6, giving us, we have a 0 at 0, and at 2 we have a 0, and at 6 we have a 0. Then what we would do is use test points on these intervals to find out, is it positive here, or in both. Between 0 and 2, if I plugged in a 1, a test point of 1 gives me a positive, negative, negative, making the values on this interval positive. Between 2 and 6, if I plug in a 5, for instance, that'd be a positive, positive, negative, giving me negative on that interval. So then what I'm going to do to evaluate this integral, I'm using this integral property that I can go from A to B and then B to C to cover this whole distance. Specifically, from 0 to 2, I'm going to evaluate it, and then from 2 to 6. But importantly, and I'll make this adjustment here in 1 second, is that on 0 to 2, the absolute value of f of x is just the same as f of x, so I can get rid of the absolute value bars on this side. On this interval, this function is equal to the opposite of it. So if I can take away the absolute values and put a negative in here. But what instead I'm going to do is, instead of put a negative on the inside, I'm going to pull it out to the outside using that constant multiple rule and make this a minus. So what I'll have is the integral of this function without absolute values from 0 to 2 minus this integral evaluated from 2 to 6 without the absolute values. So that's the whole setup. I've split up and dealt with the absolute value part. Now I just need to anti-differentiate and evaluate. These end up being exactly the same as that one over there, obviously. Rewrite this out real fast. Plus this ends up being a 6t squared. Now from 2 to 0 minus the same thing evaluated from 6 to 2. Again, I won't show all the steps in this evaluation just because mostly I want to keep this all up here and I'm running out of space. But again, I'll plug in the 2 here, plug in the 0 plays nice, then plug in the 6 and the 2 for both of those values into this antiderivative expression. When I did that, I got a value of 49.33 meters. So just to recap what we just calculated here, in the first step we found that starting from 0 seconds to ending with 6 seconds, this object ended 36 meters to the left of its original position. In the second, we started playing on this velocity function, by the way, and found out that yes, it is moving to the right and to the left. This number right here then calculates the total distance traveled to end up 36 meters to the left. By the way, while Net displacement for sure can be negative or positive depending on its location compared to original position. Distance is always a positive value, and it's the total distance. Again, taking into account that we're not going to count when velocity is negative, it doesn't mean we're going to take away. That's this move right here. We're accounting for the distance traveled when moving to the left and to the right, both as a positive value.